Welcome everyone to the first course of this channel, which is going to be about general relativity. So, as the name of the channel says, Physics for Betas, this course is going to be called General Relativity for Betas. Why for Betas? Well, the aim of this channel is to explain complex topics of physics in a much simpler and more accessible way to people who just began and haven't seen these topics previously. This channel is led by some undergraduate physics students, and I'm one of them. My name is Adrian, and I'm going to be in charge of doing all the videos for this course. So, let's start with bibliography. The two main books that I'm going to use, where I'm going to start the theory from, are these two: Space-Time and Geometry from Carroll and Gravitation and Cosmology from Weinberg. These are great books, and I highly recommend you to read them. And I also eventually use in the course some other books, which are these three. I'll use the Landau for special relativity, this one for more formal things such as manifolds, tensors, and this other book of general relativity, because there is a demonstration of something that isn't in this book, and it's, in my opinion, very useful. But the two main books are going to be this one. So what is the background that you need in order to take this course? I recommend you knowing about classical mechanics and electromagnetism, and I also brought here fluid dynamics. Well, you don't really need fluid dynamics, but we'll see that an equation reproduces in the classical limit Euler's equation, which is like the F equals ma for an ideal fluid. And we'll also start talking about the stress tensor for an ideal fluid. So if you have some background of fluid dynamics, it's good, but it's not necessary. So if you don't know fluid dynamics, don't worry. This is not very important. What is very important is calculus. So you need to know single variable calculus and multivariable calculus. And I think that if you only knew these two topics and you didn't know anything from the other, I think you could still take this course. So the most important thing here is that you need to know calculus. I also wrote here differential equations because we'll need to solve some of them, but most are going to be separable, which means that if you know single variable calculus, the kind of EDOs that we are going to encounter are going to be very, very easy to solve. So who is this course for? This course is mainly for physics undergraduates who haven't seen general relativity. Whether you are freshman, sophomore, junior, or even senior, but I think that this course is going to be more useful for freshmen and sophomore, the first and second year students. Also, if you know calculus and you are in high school, because I don't know, maybe you have done the units from Khan Academy about calculus AB, calculus BC, and also multivariable calculus, and you have done A-levels exams of calculus, and you have a strong background of calculus in high school, maybe you can take this course. So this is going to be the topics that we are going to see in this course. We'll see an introduction. We'll explain what are tensors, first in a naive way, and then we're going to see them in a more formal way here in manifolds, and we'll talk a little about classical field theory. Then we are going to introduce special relativity, which is what comes previously before GR, and we'll see the postulates, some of the basics and very important concepts, and we'll see kinematics, dynamics, and some other stuff which is really important. Then we'll start with the basics of GR. Okay, we'll see some fundamental concepts and very simple derivations that you can do before getting in all the hard math about GR. Because then we'll get into curvature, we'll see the general covariance principle, geodesics, covariance derivatives, the Riemann curvature tensor. Then we'll step in gravitation, and we'll see Einstein's field equations and all these things. Then the unit 6 is going to be the Schwarzschild solution, which is a very well-known black hole solution. Although it's not only black holes, the Schwarzschild solution applies even for planets, as long as the object that you are studying is spherically symmetrical and stationary. But we'll see this in the course. And the two last units are going to be the post-Newtonian approximation, which is like, general relativity is a very complicated theory. It's not linear, so you have to make approximations. And of course, the first approximations of general relativity are Newtonian gravitational mechanics. That's why Newton's law of gravitation works, because in the very first limit of GR, it's the first limit. So the post-Newtonian approximation is like going further to another order of magnitude of approximations. And lastly, we'll see gravitational waves, which is a propagation of energy through the gravitational field in the form of waves. So, this is going to be the course. If you are invited to give suggestions anytime in any video of the course, you are also highly encouraged to ask any doubt you have. Anytime I see any comment, I'll gladly reply to it. And I hope I see you in the course.